Linear Algebra 2, Lecture 4, Problem Session. Problem 1. Find a basis in the following subspace of R to the power 4. So the subspace V consists of all vectors x with coordinates x1, x2, x3, and x4, which satisfy the following system of linear equations. The first equation is x1 plus x2 plus x3 plus x4 is equal to 0. And the second equation is x1 plus 2x2 plus x3 plus 2x4 is equal to 0. Solution. To solve this problem, we simply need to solve the homogeneous system of linear equations with the following matrix. It's 2 times 4 matrix. And the first row is 1, 1, 1, 1. So these are the coefficients in the first equation. And the second row is 1, 2, 1, 2. So these are the coefficients in the second equation. So we start with the system matrix and we reduce it to a row echelon form using Gauss elimination. So we have 1 in row 1, column 1. So we use it to eliminate everything else in its row. So we subtract row 1 from row 2 to kill this one. Row 1 remains the same, and row 2 becomes 0, 1, 0, 1. So 1 minus 1 is 0, 2 minus 1 is 1, 1 minus 1 is 0, 2 minus 1 is 1. So now we have 1 in row 2, column 2, and we can use this one to eliminate everything else in its column. So we subtract row 2 from row 1. Row 2 remains the same, and row 1 becomes 1, 1 minus 1 is 0, 1 minus 0 is 1, and 1 minus 1 is 0. So this is now our row echelon form, which we can use to simply write down the solutions. So we start from this matrix, and we observe that the leading elements in the non-zero rows are in the columns 1 and 2. So this corresponds to the unknowns x1 and x2. So we can take all the other unknowns, that is x3 and x4, as free unknowns. And now we can use these two equations to write down the expressions for x1 and x2 in terms of x3 and x4. So the first equation reads x1 is equal to minus x3. We move this to the other side. And the second equation reads x2 is equal to the minus x4. And then for the free unknowns, we add the trivial equations that x3 is equal to x3 and x4 is equal to x4. So here is our new system of linear equations, which we can now write in the vector form. So the left-hand side of the system is the vector x1, x2, x3, x4. And in the right-hand side, we have x3 times the vector minus 1, 0, 1, 0, plus x4 times 0, minus 1, 0, 1. So now we can change x3 and x4 in the right-hand side to arbitrary parameters, let's say a and b. And so we have here the general solution to our system of linear equations. So the vector x1, x2, x3, and x4, which solves our system, is of the form a times minus 1, 0, 1, 0, plus b times 0, minus 1, 0, 1, where a and b are arbitrary real numbers. So we can directly read off the answers. Our vectors minus 1, 0, 1, 0, this vector, and the vector 0, minus 1, 0, 1, they form a basis in our subspace V. Problem 2. Show that the set n, consisting of all polynomials of degree at most 2, such that their value at 1 equals their value at minus 1, is a subspace of the set of these polynomials of degree at most 2. Find some basis in this space and determine its dimension. So first, let us prove that n is a subspace of Rx2. We need to check 3 conditions for subspaces. The first condition is that the zero polynomial should be in our subspace. This is true because the value of the zero polynomial at 1 is 0, and the value of the zero polynomial at -1 is also 0. So these two values coincide. Condition 2, let f and g be two polynomials in n. So we need to prove that their sum is in n. So let us compute the value of the sum f plus g at the point 1. By definition, this is equal to f of 1 plus g of 1. Since f is in n, f of 1 is equal to f of minus 1. Since g is in n, g of 1 is equal to g of minus 1. Therefore, we get f of minus 1 plus g of minus 1. And by definition, this is equal to the value of the polynomial f plus g at the point minus 1. So the value of f plus g at 1 is equal to the value of f plus g at minus 1. Therefore, f plus g belongs to n. And finally, condition 3, let f be a polynomial in n and lambda be a real number. Then the value of the polynomial lambda times f at 1 is by definition equal to lambda times f of 1. Since f is in n, f of 1 is equal to f of minus 1. So lambda times f of 1 is equal to lambda times f of minus 1. And again, by definition, this is equal to the value of the polynomial lambda f at the point minus 1. So lambda f at 1 has the same value as lambda f at minus 1. And so lambda f belongs to n. So all three conditions for the subspace are satisfied. Therefore, n is indeed a subspace of the vector space of all real polynomials of degree at most 2. So now let us determine a basis in n. So let f of x be an arbitrary polynomial in n, which we just write as a polynomial with unknown coefficients, a plus bx plus cx squared. So the condition f of 1 is equal to f of minus 1 applied to this polynomial reads as follows. If x is equal to 1, we get a plus b plus c. If x is equal to minus 1, we get a minus b plus c. So a plus b plus c should be equal to a minus b plus c. And so we can cancel a on both sides and we can cancel c on both sides and move b to one of the sides. So we get 2b is equal to 0, which is equivalent to the equation b is equal to 0. So now we can take a and c as arbitrary free unknowns, and we get the following system of linear equations. A is equal to a, so this is a trivial equation for the free unknown a. B is equal to 0, so this is our unique equation, and c is equal to c. This is a trivial equation for our unknown c, which is free. And in the vector form, we get that the vector ABC is equal to a times 1, 0, 0 plus c times 0, 0, 1. So in particular, we have two linearly independent solutions, and so the dimension of our vector space is 2. And as a basis, we can take the polynomials which correspond to our two linearly independent solutions. So the first solution 1, 0, 0 corresponds to the polynomial 1, the constant polynomial, and the second solution 0, 0, 1 corresponds to the polynomial x squared. So the polynomials 1 and x squared form a basis in n, and the dimension of n is 2. Problem 3. Determine all values of the real parameter a for which the following three vectors form a basis of r to the power 3. So the three vectors are the vector v1, which is 1, 1, 1, the vector v2, which is 1, 1a, the vector v3, which is 1a, a. Solution: to check whether certain vectors form a basis in r to the power 3, we need to check first of all that we have as many vectors as the dimension of r to the power 3, that is 3, and we need to check that the determinant of the matrix, which we obtain when we write these vectors as columns of the matrix, that determinant should be non-zero. Well, we have 3 vectors in R3, so that's good. We have exactly as many vectors as the dimension. So we only need to check the second condition. So we compute the determinant of the matrix where the first column is 1, 1, 1, the second column is 1, 1a, and the third column is 1a. So these are our vectors written as columns into a matrix. So this determinant is equal to 1 times 1 times a, plus 1 times 1 times a, plus 1 times 1 times a, minus 1 times 1 times 1, minus 1 times 1 times a, minus 1 times a times a. So if we add all these things, we will get minus a squared coming from here, plus 2a coming from here, this and this term cancel, and then minus 1. And this is minus a minus 1 squared. So this expression is non-zero if and only if a is different from 1. So answer to our problem is that our 3 vectors v1, v2, and v3 form a basis in R3 if and only if a is different from 1. Problem 4. Let M be the linear span of the following vectors in R to the power 4. The vector v1 is 1, 1, 0, 1. The vector v2 is 2, 2, 0, 2. The vector v3 is 1, 0, 1, 0. The vector v4 is 2, 1, 1, 1. The vector v5 is 0, 1, minus 1, 0. And the vector v6 is 1, 2, minus 1, 2. First assignment. Determine a basis in M consisting of sum of these vectors. Second, determine the coordinates of all of these vectors in this basis. And third assignment is to determine all values of the real parameter a for which the vector w, which is equal to a, 2 minus a minus 1, a, belongs to M, and for all such values of this parameter a, determine the coordinates of the vector w with respect to the basis from the first part of the problem. Solution. To solve part 1, we need to write our vectors as columns in a matrix and reduce this matrix to a row echelon form. So the basis would correspond to the leading elements in the non-zero rows of the row echelon form. If we solve part 1, then all other parts translate into solving a system of linear equations where our basis vectors are on the left-hand side and the vector for which we try to determine the coordinates is on the right-hand side. Which means that we can solve all parts of our problems at one by writing all our vectors as columns in one matrix and reducing this matrix to a row echelon form using Gauss elimination. So we solve all parts of the problem in one go. So we consider the following matrix. So here v1 is the first column, v2 is the second column, v3 is the third column, and so on. And then we draw a vertical line and we write the vector w as the last column of the matrix. So here the vertical line signifies the fact that the subspace which we are working with is generated by all the vectors which are to the left of this line, and we cannot take w into the generating set of our subspace. So we start from this matrix and we reduce it to a row echelon form using Gauss elimination. So we have 1 in row 1, column 1, so we can use it to kill all other elements in this row. So we subtract row 1 from row 2 and we subtract row 1 from row 4. Row 1 and row 3 remain the same. Row 2 becomes 1 minus 1 is 0, 2 minus 2 is 0, 0 minus 1 is minus 1, 1 minus 2 is minus 1, 1 minus 0 is 1, 2 minus 1 is 1, 2 minus a is 2 minus 2a. And the last row becomes 1 minus 1 is 0, 2 minus 2 is 0, 0 minus 1 is minus 1, 1 minus 2 is minus 1, 0 minus 0 is 0, 2 minus 1 is 1, and a minus a is 0. So now we have 1 in column 3, in row 3. So let us change the second and the third rows. So the first row remains the same, the last row remains the same, and the second and the third rows, they just swap. So now we have 1 here in row 2, column 3. We can use this one to kill all other elements in the third column. So we subtract row 2 from row 1, and we add row 2 to both row 3 and row 4. So row 2 remains the same. Row 1 becomes 1 minus 0 is 1, 2 minus 0 is 1, 1 minus 1 is 0, 2 minus 1 is 1, 0 minus minus 1 is 1, 1 minus minus 1 is 2, a minus 1 is just plus 1. Okay, row 3 becomes 0 plus 0 is 0, 0 plus 0 is 0, 1 plus minus 1 is 0, 1 plus minus 1 is 0, minus 1 plus 1 is 0, minus 1 plus 1 is 0. A minus 1 plus 2 minus 2a is 1 minus a. And the last column becomes 0 plus 0 is 0, 0 plus 0 is 0, 1 plus minus 1 is 0, 1 plus minus 1 is 0, minus 1 plus 0 is minus 1, minus 1 plus 1 is 0, a minus 1 plus 0 is a minus 1. So now we have this minus 1 here in row 4 and column 5. We can multiply it with minus 1 and then swap with row 3 to get 1 here. So rows 1 and 2 remain the same. Row 3 moves to row 4, and the new row 3 becomes 0, 0, 0, 0, 1, 0, 1 minus a. And now we can use 1 in the fifth column, the third row, to kill everything else in the fifth column. So we subtract row 3 from row 1 and we add row 3 to row 2. Rows 3 and 4 remain the same. Row 1 becomes, so the first 4 elements remain the same, and then 1 minus 1 is 0, 2 minus 0 is 2, 1 minus a is a. And row 2, the first 4 elements are the same, and then 1 plus minus 1 is 0, 0 plus minus 1 is minus 1, a minus 1 plus 1 minus a is 0. So here is our row echelon form. So we look at this matrix and we can now read off all answers. So first of all, if we just look at the first 6 columns, we see that in the non-zero rows, the leading elements are in the columns 1, 3, and 5. This means that the vectors v1, v3, and v5, the vectors which correspond to these columns, they form a basis in M, and we denote this basis by v. The columns which we now see in this matrix are exactly the coordinates of all other vectors in this basis. So the coordinates of the vector v1 in our new basis is 1, 0, 0. The coordinates of v2 are 2, 0, 0. The coordinates of v3 are 0, 1, 0. The coordinates of v4 are 1, 1, 0. The coordinates of v5 are 0, 0, 1. And the coordinates of v6 are 2, minus 1, 0. And now we can look at w. The vector w will be in the linear span of v1, v3, and v5 if and only if the rank of the total matrix is the same as the rank of the matrix without the right column. In other words, this entry here in row 4 and the last column, it should be 0. So w belongs to M if and only if a is equal to 1. And in this case, the coefficients here are the coordinates, in which case the coordinates of w in the basis v are 1, 0, 0. So this completes problem 4. Problem 5. Let n be the linear span of the following polynomials in Rx3. f1 is 1 plus x squared, f2 is 2 plus 2x squared, f3 is 1 plus x squared plus x cubed, f4 is 2 plus x plus 2x squared plus x cubed, and f5 is 2 plus 3x plus 2x squared plus 3x cubed. Determine a basis in N consisting of some of these polynomials. Extend this basis to a basis of Rx3. Solution. We have the standard basis in Rx3 consisting of the polynomials 1, x, x squared, and x cubed. So to solve the first part of the problem, we should write the matrix, which consists of the coefficients of our generating polynomials written as columns in this matrix, and the coefficients should be taken with respect to the standard basis. So we should start from this matrix and reduce it to a row echelon form using Gauss elimination. And the leading coefficients in non-zero rows then will correspond to bases in N. And to solve the second part of the problem, we should at the same time add the elements from the standard basis additionally to our matrix, and then reduce everything to a row echelon form, and then look where the leading coefficients will be, and those vectors form a basis in the whole space. So again, we solve the whole problem in one go. So we start from the matrix, where on the left-hand side of the vertical line, we have the coefficients of our 5 generating polynomials written as columns in a matrix, and these are the coefficients with respect to the standard basis. And on the right-hand side of the vertical line, we have the coefficients of the standard basis elements in the standard basis. This means we just write the identity matrix. And now we have to reduce this matrix to a row echelon form using Gauss elimination. So we have 1 in row 1, column 1. So we use it to kill all our elements in this column. And we see we have 1 here in row 3, so we simply subtract row 1 from row 3. Row 1, 2, and 4 remain the same, and row 3 becomes 1 minus 1 is 0, 2 minus 2 is 0, 1 minus 1 is 0, 2 minus 2 is 0, 2 minus 2 is 0, 0 minus 1 is minus 1, 0 minus 0 is 0, 1 minus 0 is 1, 0 minus 0 is 0. So this is our new matrix. Now we have here in row 2, column 3, 1. We should now use this 1 to kill everything else in this column. We don't need that much. We actually need only to kill everything which is below this 1. So we simply subtract row 2 from row 4. Rows 1, 2, and 3 remain the same, and row 4 becomes 0 minus 0 is 0, 0 minus 0 is 0, 1 minus 1 is 0, 1 minus 1 is 0, 3 minus 3 is 0, 0 minus 0 is 0, 0 minus 1 is minus 1, 0 minus 0 is 0, 1 minus 0 is 1. And now we see that our matrix is more or less in the row echelon form. So we have this matrix with leading elements being in columns 1, 3, and then also after the vertical line we have column 6 and 7. So now we just read off the answer to our problem. First, let us look at the part of the matrix to the left from the vertical line. The leading elements in the non-zero rows are in columns 1 and 3. This means that the polynomials f1 and f3 form a basis in N. If we look in the whole matrix, then we see that the leading elements are in the columns 1, 3, 6, and 7. These columns correspond to f1, f3, the polynomial 1, and the polynomial x. Therefore, the polynomials f1, f3, 1, and x form a basis of the vector space of all polynomials of degree at most 3. And we see that this basis extends our chosen basis in N. Problem 6. Consider the following vectors in R3. The vector v1, which is 1, 1, 1, the vector v2, which is 2, 1, 1, the vector v3, which is 2, 2, 1, the vector w1, which is minus 1, 1, 1, the vector w2, which is 1, 1, 2, and the vector w3, which is 1, 2, 1. Part 1. Show that the collection V of the vectors v1, v2, and v3 is a basis of R3. Part 2. Show that the collection W of W1, W2, and W3 is a basis of R3. Part 3. Determine both transformation matrices from V to W and from W to V. And part 4. For the vector x, which is equal to 3, 2, 2 in R3, determine the coordinates of this vector with respect to both V and W. Solution. We know that the dimension of R3 is 3. And both collections V and W consist of 3 vectors. So that's good. So to solve the first two parts of the problem, to prove that they are bases, we need to check that the determinants which we get when we write those vectors as columns in a square matrix, those determinants should be non-zero. So the first determinant for the collection V is the matrix column-wise 1, 1, 1, 2, 1, 1, and 2, 2, 1. So these are the vectors v1, v2, and v3. So this determinant is equal to 1 times 1 times 1, plus 2 times 2 times 1, plus 1 times 1 times 2, minus 2 times 1 times 1, minus 2 times 1 times 1, minus 2 times 1 times 1. And when we compute this, we get 1, which is non-zero, and this implies that V is a basis in R3. The second determinant is the matrix column-wise minus 1, 1, 1, 1, 1, 2, 1, 2, 1. So these are our vectors W1, W2, and W3. So this determinant is equal to minus 1 times 1 times 1, plus 1 times 2 times 1, plus 1 times 2 times 1, minus 1 times 1 times 1, minus 1 times 1 times 1, and minus 1 times 2 times 2. When we compute this, we get 5, which is non-zero, and this implies that W is a basis of R3. To determine the transformation matrix from V to W, we need to find the coordinates of the vectors W1, W2, and W3 in the basis V and write them as columns into a matrix. So this problem basically reduced to finding the coordinates of W1, W2, and W3 with respect to the basis V. And we additionally also need to find the coordinates of x with respect to the basis V. So we need to solve the problem where the left-hand side is a matrix consisting of vectors v1, v2, v3, and then the right-hand side consists of, we have 4 different problems. The first problem is for w1, the second for w2, the third is for w3, and the fourth is for x. And again, we write one big matrix and solve all these problems in one go. So here we have the matrix for v1, v2, v3. Here we have the matrix for w1, w2, and w3. And here we have a column for x. So we reduce this matrix to a row echelon form using Gauss elimination. So we have 1 here. We use this 1 to kill everything in the first row. So we subtract row 1 from row 2, and we subtract row 1 from row 3. Row 1 is the same, and then row 2 becomes 1 minus 1 is 0, 1 minus 2 is minus 1, 2 minus 2 is 0, 1 minus minus 1 is 2, 1 minus 1 is 0, 2 minus 1 is 1, 2 minus 3 is minus 1. And the row 3 becomes 1 minus 1 is 0, 1 minus 2 is minus 1, 1 minus 2 is minus 1, 1 minus minus 1 is 2, 2 minus 1 is 1, 1 minus 1 is 0, and 2 minus 3 is minus 1. So now here we have here minus 1, so we multiply the second row with minus 1 to get 1 here. Rows 1 and 3 remain the same, and row 2 becomes 0, 1, 0, minus 2, 0, minus 1, 1. So now we use this 1 to kill everything in the second column. So we multiply row 2 with minus 2 and add to row 1, and we also add row 2 to row 3. Row 2 remains the same. Row 1 becomes 1 minus 0 is 0, 2 minus 2 is 0, 2 minus 0 is 2, minus 1 minus 2 times minus 2, it's plus 4, is 3, 1 minus 0 is 0, 1 plus 2 is 3, 3 minus 2 is 1. And the last row is 0 plus 0 is 0, 1 plus minus 1 is 0, 0 plus minus 1 is minus 1, 2 plus minus 2 is 0, 1 plus 0 is 1, 0 plus minus 1 is minus 1, 1 plus minus 1 is 0. And now we have minus 1 here, so we multiply the last row with minus 1. The first two rows remain the same. The last row becomes 0, 0, 1, 0, minus 1, 1, 0. And now we need to kill this 2 using this 1, so we multiply the last row with minus 2 and add to row 1. Rows 2 and 3 remain the same, and row 1 becomes 1 minus 0 is 0, 0 minus 0 is 0, 2 minus 2 is 0, 3 minus 0 is 3, 1 plus 2 is 3, 3 minus 2 is 1, 1 minus 0 is. So now here is the row echelon form, and we have all answers in this matrix. So the transformation matrix from V to W is this matrix, because these are the coordinates of W1, W2, and W3 in basis V. So this transformation matrix is 3, 3, 1, minus 2, 0, minus 1, 0, minus 1, 1. And this column consists of the coordinates of x in basis V. So the coordinates of x and v are 1, 1, 0. So now we need to find the transformation matrix in the opposite direction from W to V, and we know that this is simply the inverse of the transformation matrix from V to W. So to find an inverse of the matrix, we write this matrix, here it is, vertical line and then the identity matrix. And now we need to reduce this to a row echelon form using Gauss elimination. So we have here in the first column, we have 3 and minus 2. If we add them up, we will get 1. So we add row 1 and row 2 and write in row 1. Rows 2 and 3 remain the same, and row 1 becomes 3 plus minus 2 is 1, 3 plus 0 is 3, 1 plus minus 1 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0. So now we have 1 here, so we use it to eliminate everything else in the first column. So we multiply row 1 with 2 and add to row 2. Rows 1 and 3 remain the same. Row 2 becomes 2 minus 2 is 0, 6 plus 0 is 6, 0 plus minus 1 is minus 1, 2 plus 0 is 2, 2 plus 1 is 3, 0 plus 0 is 0. Now here we have minus 1 in column 2, but in row 3. So we multiply row 3 with minus 1 and swap it with row 2. So row 1 remains the same, row 2 becomes row 3, and new row 2 is minus the previous row 3. It's 0, 1, minus 1, 0, 0, minus 1. So now we use 1 here to kill everything else in column 2. So we multiply the second row with minus 3 and add to row 1. We multiply the second row with minus 6 and add to row 3. So row 2 remains the same. Row 1 becomes 1 minus 0 is 1. 3 minus 3 is 0. 0 plus 3 is 3. 1 minus 0 is 1. 1 minus 0 is 1. 0 plus 3 is 3. And the last row becomes 0 minus 0 is 0, 6 minus 6 is 0, minus 1 plus 6 is 5, 2 minus 0 is 2, 3 minus 0 is 3, 0 plus 6 is 6. So now we have 5 here. We have no choice. We have to divide by 5. So we divide the last row by 5. The first two rows remain the same, and the last row becomes 0, 0, 1. 2 divided by 5, 3 divided by 5, 6 divided by 5. So now we can use this one to kill everything else in the third column. So we add row 3 to row 2, and we multiply row 3 with minus 3 and add to row 1. So row 3 remains the same, and row 1 becomes 1 minus 0 is 0, 0 minus 0 is 0, 3 minus 3 is 0, 1 minus 6 divided by 5, minus 1 divided by 5, 1 minus 9 divided by 5, it's minus 4 divided by 5, and then 3 minus 18 divided by 5. So 15 minus 18, it's minus 3 divided by 5. So the first row is minus 1 divided by 5, minus 4 divided by 5, minus 3 divided by 5 here. And the second row, it's 0, 1 plus 0 is 1, 1 plus minus 1 is 0, and then 0 plus 2 divided by 5 is 2 divided by 5, 0 plus 3 divided by 5 is 3 divided by 5, minus 1 plus 6 divided by 5 is 1 divided by 5. So here on the right-hand side of the vertical line, we have 2 divided by 5, 3 divided by 5, and 1 divided by 5. So the transformation matrix from W to V is what is on the right-hand side here. It's 1 divided by 5 times the matrix minus 1, minus 4, minus 3, 2, 3, 1, 2, 3, 6. And using the base change formula, the coordinates of x with respect to W are equal to the transformation matrix from W to V times the coordinates of x with respect to V. So we take our matrix 1/5 times minus 1, minus 4, minus 3, 2, 3, 1, 2, 3, 6, times the coordinates 1, 1, 0. So these are the coordinates of x with respect to v, which we already computed. So now if we multiply, we will get the first coordinates minus 1, minus 4. It's minus 5 divided by 5. We get minus 1. The second coordinate is 2 plus 3 divided by 5. This is 1. And the last coordinate is 2 plus 3 divided by 5, which is 1. And this completes problem 6. Here are some other problems. Question 1. Let V be a finite dimensional vector space and W a subspace of V. Show that the dimension of W is at most dimension of V. Question 2. Let V be the space of all polynomials of degree at most 3. Let W be the set of all polynomials in V such that f of 2 is equal to f of 3. Shows that W is a subspace, find some basis in this subspace, and determine its dimension. Question 3. Show that the polynomials 1 plus x to the power k, where k is equal to 0, 1, 2, and 3, form a basis in Rx3, and determine the coordinates of the standard basis elements in this new basis. Question 4. Find the transformation matrix from the basis 1 plus x to the power k, where k is 0, 1, 2, to the basis x minus 2 to the power k, where k is 0, 1, and 2, of Rx2. And question 5. Find some basis in the subspace of all polynomials of degree at most 3, such that f of 1 is equal to f of 2 is equal to 0. This is a subspace of Rx3, and extend this basis to a basis of Rx3. Thank you very much, and see you next time.